The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, ladies and gentlemen. Welcome to TechGig webinar series, our endeavor to empower techies. We believe that sharing of knowledge is the key to enhance our skills and grow us as professionals. With this principle in mind, we have initiated a sense of webinars conducted by industry experts to give you all a crisp insight of various domains. The topic of today's session is real-time big data analysis using Cloudera Impala. And our guest speaker today is Mr. Muthu Kumar. He's the member of technical staff with eBay. Muthu Kumar has obtained the MSc by Research degree from Distributed and Object System Lab, Indian Institute of Technology, Madras in 2005. He is currently working at eBay, focusing on the area of big data analytics and SOA. He also worked in the area of building application frameworks, application management in distributed heterogeneous environment. His area of interest including program languages, parallel and distributed computing, system software and object technology. So without further delay, I introduce you all to our guest speaker. Over to you, Muthu Kumar.
Okay, sure. Thank you, Aradhana. Good afternoon, everyone. So I'm Muthu from eBay. So in this session today I'm going to talk about real-time big data analysis using Cloudera Impala. So let's start the presentation. Okay, so let me skip the disclaimer slide. Okay, so here is the agenda. So Impala, just one second. Am I audible?
Yes. Yes, Muthu Kumar, you are audible.
Am I audible?
The audience can hear you loud and clear.
Hello, Aradhana. Am I audible?
Muthu Kumar, we can hear you. Can you hear me? Muthu Kumar, can you hear me?
Yeah, I can hear you. Am I audible now?
Yes, your voice is loud and clear. You can continue with your presentation.
Sure, thank you. Okay, so today we are going to talk about real-time big data analysis using Cloudera Impala, and so I'm in agenda slide. Okay, so here is the agenda. So Impala is a Cloudera product. First, let me talk about why we picked Impala for real-time big data analysis when we started the experiment. Then we talk about Impala architecture overview, and finally I will share my experience with Impala and present the experimental results. Okay, I'm going to the next slide. Yeah, so basically, second. Yeah, so okay, so here is the scale at which we operate at eBay. There are 120 million active users in eBay, and there are 100 billion database call read and write operations executed every day. So, and we have 3.5 trillion rows in the largest table, and 100 plus terabytes of data coming to our system every day. So, doing real-time analysis over this big data is a real challenge. And I'm moving to the next slide. Okay. So now here are the big questions that we had when we started working on real-time big data analysis. So in the previous slide, we saw that 100 plus terabytes of new data coming to our system every day. So how do we run analytical queries over petabytes of data in near real time? Let me take an example and explain this. As you all know that eBay is a marketplace, and we connect buyers and sellers. Say sellers want to know which city in Texas bought most from them. So how do I get this result in real time? Sellers can't wait for hours to get the results, so they would like to get the results immediately. So how do we run the analytical queries over the petabytes of data in near real time? Okay, the next question is how do we achieve the low latency response with minimal effort? Basically, we don't want to go through an extensive ETL process. So ETL is basically extract, transform, and load. It is typically used in data warehouse environment. If for example, the ETL phase, in the extract phase, what happens is the data is extracted from multiple sources. In the transform phase, the extracted data will be transformed to suit the target system. So for example, joining the data from multiple data sources. And this data will be transformed in such a way that it is easy to run analytical queries over the data. And in the load phase, what happens is the transformed data will be loaded into target system. Typically, it will be in a data system. And finally, the analytical queries will be running on the target system. So basically, we don't want to go through this extensive ETL process to run the analytical queries. And so what we have is we have all the data available in relational databases. And how do we export these data into new system with minimal effort and run analytical queries? So what I'm trying to say is basically we don't want to massage the existing data. And the next question is there any cost-effective solution available to run the analytical queries? So basically we can keep adding the servers to RDBMS system and run the query that we want. But that is very expensive. So relational database will not scale beyond a point. So we need a cost-effective solution to run the analytical queries. Okay, so now let's look at what are the options available currently to run the analytical queries and drawbacks of each option. We will discuss the drawbacks of each option. So now I'm in slide, can we use MapReduce? So can we use MapReduce? So that's a question. And as you all know that Hadoop is the open source framework for storing and processing large scale distributed data on a cluster of commodity hardware. And MapReduce is a programming model for large-scale data processing. So let me take an example and explain how MapReduce works. So as you can see in the slide, here is a popular word count example. So this example reads the text files and count how often a word occurs. So as you can see that each text file, we have a big data in the background. And each text file goes to a different machine, and mapper functions run on these machines and split the words. So as you can see that the file which there was John was, hi John, all those things. So each file goes to a mapper machine, and mapper function run on these machines and split the words. Okay, and then so once the mapper function executed, so it emits the key value pair of the word and one. For instance, here you can see that John and 1. So you can see that John and 1. John is the key and 1 is the value. Okay, so when the mapping phase has completed, the intermediate that is the key value pair must be exchanged between machines to send the values with the same key to a single reducer. So for example, so you can see here, once the mapper function is completed, so all the intermediate values will be exchanged to a single reducer machine. I mean, all the same keys will go to a single reducer machine. So you can see that here. The network is slow. So you can see that John 1, there are 3 John 1s. All 3 John 1 will go to a single machine. That is the second reducer machine. So once the key value pairs reach the reducer, so what happens is a reducer run on each machine and count the number of words using each key value pair. And so finally it will output the number of words for each key. So the problem here is that the intermediate results are written into a disk. So for instance, the mapper outputs, the intermediate plot and tuple outputs, reducer outputs, etc. are written into disk. So this is because of this I/O, the existing MapReduce based system is not suitable for running real-time queries. So, so the I/O is really costly. There is a saying that the fastest I/O is the one that never takes place. So the existing MapReduce system is not suitable for running real-time queries. So instead, it is suited for running batch-oriented applications. So we have seen the Hadoop system in the previous slide. I mean, how Hadoop system can be used for the batch-oriented applications, not for the real-time applications. So now I'm going to talk about the other existing similar technologies. So as you can see that there are other existing technologies like Hive, HBase, Cassandra, and MongoDB for running queries on large-scale data. So the problem is those are either don't support joins, or it is very slow, or it is optimized for read and write operations, or there is no SQLite feature in these technologies. So basically, these existing systems are built for a specific purpose, and they have some drawbacks, as I mentioned before that. Okay, so now let me talk about why we picked Impala. So as I talked in the previous slides, MapReduce is too slow for running real-time queries, and it is ideally suited for batch-oriented applications. And there are other options available to run the analytical query, like a remote query that I mentioned in the slide. So here what we do is we pull data from HDFS over the network to the data warehouse compute layer and run the analytical query in data warehouse compute layer. Since we run the queries in data warehouse compute layer, it is slow and it is very expensive. So basically, what we are looking at is we are looking at something very similar to relational databases. See, most of us are familiar with relational database features, so it would be good if some system mimics the most of the functionalities of RDBMS. And we thought Impala is the perfect fit in that aspect. So basically, Impala is a native, massively parallel processing engine that is integrated in Hadoop, and let's look at more about Impala in this slide. So as I mentioned previously, it is an in-memory distributed SQL query engine, and it is primarily built for running low latency analytical queries. And it is built on top of Hadoop, so it is highly scalable. It is not that it is entirely built from the scratch, but it is built on top of Hadoop. So it is simply scaled by just adding nodes. Say for example, I start with 10 machines initially, and my data and processing requirement grows. Adding more machines will take care of my load. So that means that we also need to avoid data movement across the nodes. You know? So if we simply add machines and have too much of data movement across the nodes, then it defeats the purpose. So we should do as much as local processing as possible, and Impala does all that. So let's look at more about that in the upcoming slide. Okay, so and the other point is it is easy to use. Only minimal data transformation effort is required here when you use Impala. You can use it just like your RDBMS relational database system. Since it supports join, you don't need to massage the data to suit the target system. So if you have your data in relational database, all you need to do is just pour the data into HDFS and start using with Impala. So, and you have SQL support available with Impala, so you don't need to write any code for processing the data like MapReduce that you do. And since it supports JDBC client, it is easy to integrate into a Java-based client. And also it's cost effective because it runs on commodity hardware. The cost comes down drastically, unlike the relational database. Okay, so on the next slide. Okay, so and as you can see that Impala is really fast. So we'll show you the results in a couple of slides. So in the existing MapReduce system, what happens is the analyst execute a query and wait for minutes or hours to get back the result. So what they typically do is they do some other task till the result comes back. So once the result comes back within minutes or hours, then they think what to do next. And this context switching becomes a big problem. So if you get the results in seconds, it is easy to iterate through the results and execute the next query. So basically, to summarize why we picked Impala, the Impala is highly scalable because it is built on top of Hadoop, and it's an in-memory distributed query engine, and it's really fast. And it has direct access to HDFS. There is no MapReduce involved in this, and you can use it just like your relation database, and you can do joins. All those SQL features are available with Impala. Okay, this is the reason why we picked Impala. Okay, now let's look at the architecture part. Okay, so here is the architecture of Cloudera Impala, and okay, so let's look at the unified metadata store, which is depicted on the top corner of the slide. You can see that. So basically, Impala uses Hive metastore. So Hive is something similar to Impala. So the only difference is when you execute a SQL query, Hive converts the query into a series of MapReduce programs. So it internally uses MapReduce programs, and since it uses MapReduce program, it is very slow. So basically, what Hive gives you is it gives you an abstraction over the existing programming model available in Hadoop. So, but Impala uses only the Hive metastore to store the metadata. So other than that, it doesn't use anything in Hive. So basically, Impala table is physically represented as data files in HDFS. So that's a Hadoop distributed file system. So, so what happens when you create a table in Impala? So when you create a table in Impala, there is a mapping created between tables and files. So this mapping is stored in Hive metastore, and the mapping between files and actual blocks in the disk is stored in the name node. So basically, Impala uses both Hive metastore and name node to store the metadata, and this will be used when you execute a query. So as you can see in the slide, there are data nodes depicted in the slide. So Impala is a daemon which is running on each node, where the actual data resides in HDFS. Okay, so as you can see, the Impala daemon will be running on each data node as depicted in the slide. And the Impala daemons are in constant touch with state store. There is something called Impala state store. So it will be in constant touch with the state store, which will maintain the health of each domain. So basically, when you fire a query, the Impala daemon will connect to the metastore as well as the state store to get the metadata and to get to know the status of each Impala daemon. Okay, so we have looked at the Impala daemon at a higher level. So now let's look at deep about the Impala daemon itself. So Impala daemon has 3 components, as you can see in the slide. So there are 3 components: query planner, query executor, and query execution engine. Initially, a client connects to Impala D and sends SQL query request, and the query planner gets the file location details from metadata cache. So basically, it finds out where the data is and when you execute a query. Then it gives the plan to the query coordinator. So as you can see in the slide. So once the query coordinator gets a plan, it calls the corresponding query execution engine based on the plan. And the query execution engine is the one that actually executes the query. So basically, we have seen the internal components of Impala: the query planner, query executor, and query execution engine. So now let's look at the file system. So for Impala, the primary data source is HDFS. So HDFS, as you all know, that it's a Hadoop distributed file system. And Impala relies on the redundancy product by HDFS to guard against hardware or network outages on individual nodes. So Impala table data is physically represented as data files in HDFS using familiar HDFS file format. So like text format, pocket format. So I'll talk about the pocket format in later slides. It can also read from HBase if your data resides in HBase. So basically, you can execute your query in any of the data nodes since Impala is running on each machine. Say for example, you execute a query on a node A. Node A's query coordinator is responsible for collecting the intermediate results from the other nodes and give back the result to the client. So this is the high-level overview about Impala architecture. Okay, now let's look at what happens behind the scenes when we execute a query. Okay, so first let's look at how join works between the tables. So what happens in Impala is the largest table should be listed first in the from class of a query. So you write a query and you have a join between multiple tables. So the largest table should be listed first in the from class. But this ordering will be automatically handled in the recent version of Impala. Basically, the join order also matters when you execute a query. So the largest table should be listed first. But this ordering will be taken care in the recent version of Impala. And so the default join type supported by Impala is broadcast type. So in broadcast join, what happens is, so you join between left table versus the right table. So the right table's data will be broadcasted to the nodes where left table data is there, and join will occur locally in the nodes where left table data is there. So for example, you're joining between a table A and B. So here what happens is the largest table should be A and the small table will be B. So what happens here is the data of table B will be broadcasted to the nodes where the data A's table is there. And the join will happen on the node where the node table A's data is there. And as you can see that the important point is it doesn't write the intermediate results into disk. Instead of that, its join will happen in memory. So the memory of the node should be capable of holding the right table data. And this is the limitation currently. So however, this limitation is resolved in other supported joins in Impala. Okay, so this broadcast join type is best suited for single largest table and multiple small tables. So now let's take an example and see how query execution happens in Impala. So here is the example query, and so what this query does is that in California and New York, on a particular brand that is priced between 100 and 200, how many items are available? So that's all the query does. So it's a join between three tables: store sales, store, and item. So you can see that predicates are here: list price, which is in store sales between 100 and 200. Then state, which is in store table in California and New York, and the brand is some value. And finally, what happens is it groups by state and the brand. So as you can see in the query, SS represents store sales, and S represents stores, and I represents item table. Okay, so now let's look at how it executes the query. So first, what happens is the store sales data, the store sales metadata will be retrieved, and the condition list price between 100 and 200 will be executed in relevant nodes. So similarly, what happens is a store and item tables predicates will be executed, as you can see in the slide. So now after executing all three predicates, the join will be executed. So in the first join, what happens is the join will be executed between store sales and store. So once the store predicate is evaluated, the intermediate results are streamed back to the nodes where store sales data are there. And join will happen locally where the store sales data is there. So as you can see in the slide, similarly the join between store sales and item tables will be executed using broadcast join that I explained in the previous slide. And so once the join is completed, finally group by state and brand will be executed and the result will be returned back to the client. So this is how the Impala executes the query. So I'm going to the next slide. So as I explained previously, Impala does not put the intermediate results into disk. Rather, it will execute everything in memory, including the joins. So the problem is when you join between two large tables, what happens is the broadcast join may not work because so you can't join a large table in memory, right? So for that case, there is something called partition join they support. So in the partition join, what happens is both left table data and the right table data will be exchanged between the nodes. So that way they're resolving this memory issues. Okay, so now let's look at the benchmarks. So we have two tables here, fee table and the order table. And fee table has around 20 million transactions. So these are just one seller data. And as you can see that the size of the data is 345 MB. It's a compressed one. And without compression, it takes about, I think it's about 30 GB. So with compression, it takes about 345 MB. And the data format of fee is Parquet format. So Parquet is basically a compressed columnar storage format for Hadoop. And it performs well for most of our use cases. And the second table is order table. It has about 1 million transactions. And the size of the table is 216 MB. And the format is text files because the size is very slow. We didn't go ahead and compress the data. Okay, so basically, so what we have is we have experimented this with two tables, fee tables and the order table. So now let's look at what query is executed when you fetch the fees. So here in this query, what we do is so we get the total fees, the number of shipping charges, and the shipping cost. So as I mentioned in the slide, it is FedEx and GSP. So those are the shipping charges and shipping costs. And here the data is partitioned by date. So in the predicate, you can see that the predicate is based on the account number and the partition numbers. So basically in the query, fee query, what we do is we get the total fees, the number of shipping charges and the shipping cost itself. Okay, now let's look at the order details query. What happens when you fire a query to fetch the order details? So as you can see that we get the total sales amount, average item price, and the sum of quantity based on the seller ID, data, and the currency ID, date and currency ID. So that's what we do in the order details. And for the join query, what happens is so we take the total sales amount and the count in the state Texas for a particular fee type. So that's what we do in the join query. So we basically join the fee table and the order table in the join query. Okay, now let's look at the performance result. So we are presenting the result for the first run and the subsequent runs. So when you run the query for the very first time, it is without cache. And as a subsequent run, the Impala will use the OS cache to buffer the already retrieved data. So here the cache performance is important because you are very likely to run the query which will slice and dice on the data that is just retrieved in the previous query. So even the cache data is very important here. So as you can see in the free query, it takes about 1.95 seconds for the first run, and on the subsequent run it takes about 1.57 seconds. And the order details table takes about 0.46 seconds, and on the subsequent run it takes about 0.38 seconds. And coming to the join query performance, the join for the first run it takes about 1.74 seconds, and the subsequent run it takes about 1.48 seconds. So basically, even for the join, it performs very well. So you can see that. Okay, so now let's look at the load test that we have done with Impala. It's actually slow. Okay. So it's getting loaded. So what I'm going to talk about is the setup initially, and then I'm going to present the results of the load test. Okay, so here is the setup that we had. So we had about 1 year fee transaction for 600K seller accounts, and all the 600K accounts are loaded into Impala, and fee query is used as a benchmark. So I explained about the fee query in the previous slide. So data is partitioned by the account number. So what happens is each account or group of accounts will go to one particular partition. So here we tested with two cluster setup. One is with 10 node cluster and other one is 20 node cluster. So data is loaded into both the clusters. Just to measure the scalability, we tested with multiple clusters. Okay, so now let me talk about the parallel processes. So as you can see in the slide, we tested with 50, 100 and 200 processes running in parallel. So for example, here is the execution plan for 100 processes. In 20 node cluster, each node executes 5 processes, and each process handles a set of accounts. Similarly, in 10 node cluster, what happens is each node executes 10 processes, and each process handles a set of accounts. So basically, the load is divided between the nodes in the cluster. So that's what I'm trying to say. Okay, now let's look at the load test results. So as you can see in the slide, if we increase the number of nodes, the performance automatically increases. So as you can see that for the 10 node cluster, say 100 processes, it takes about 1.9 seconds. For the 20 node, it takes about 1.3 seconds. So as you increase the number of nodes, the performance increases. So as well as you increase the number of processes, the performance comes down. Because as of now, what happens is in Impala, the number of threads created by Impala is not configurable at this point of time. So by default, it creates about 2 to 3x number of threads, number of cores basically. So suppose I have a 4-core machine, it creates about 12 threads in a machine. So this number of threads created by Impala is not configurable. So we are not able to test the Impala by increasing the number of threads. So that's why the performance degrades when you increase the number of processes. But as you can see that it just scales when you simply add nodes, just like in Hadoop. The performance increases. Okay, so now let's look at how we transition to Impala. So assuming that you have all the data in relational databases and you want to use Impala, so what you can do is you can use there is a tool called Apache Scoop. and you can use Apache Scoop to transfer data between relation database and Hadoop, and then you can start using Impala straight away. So basically, when your data is in relation database, there is a tool provided by Apache called Apache Scoop, which you can use to transfer the data between relation database and Impala. So this is one use case. Another use case is assuming that you already created tables using Hive and you already have a Hadoop setup with you. So in that case, all you need to do is just install Impala and straight away you can start using it. Because Impala internally uses Hive Metastore, so you can straight away start using the Impala. So since it's built on top of Hadoop, it is easy to use because so most of us might be working on the analytical queries, the batch-oriented application using Hadoop already. So if you have the setup ready, you can straight away use the Impala. Okay, so here are the learnings that we had from our experiments. The first point is Impala is a good choice for running interactive queries on a big data, which needs real-time response. So if you need a real-time response and you want to run an interactive query on a big data, so Impala is a choice. And it scales well for hundreds of users on small clusters. That's what we tested. And as far as our use case is concerned, Parquet columnar format performs better than other existing formats. So we tested with other formats like text file format, RC file format, other things. So out of other existing formats, the Parquet format performs better than for our use case. Okay, that concludes the presentation, and as you can see here, the useful links for the Cloudera, so you can Impala, so you can go through the notes available in this website. Okay, thank you for attending the presentations, and now if you have any questions, you can answer that now.
Thanks for the insightful presentation. Let's quickly take up the questions now. I request you to read out the questions and their answers so that all our users may listen to your insights. So are you able to see the questions that might have come to your questions doc, Muthukumar?
Yeah, so okay, so I'm seeing one by one, and just let me read out the question. Okay, let me read out the first question. So actually the input to reduce would be the key and the list of values wouldn't be. So I talked about the example for the MapReduce. So basically the key value pair is the key is the actual word and the value is it is just one. It is not the list of values. So when I explain the example, so basically there are the same word is appeared in 3 keys. The John example that I explained. So all these 3 same keys will go to a single reducer, and the reducer will compute the number of times the word occurred. So basically, it is not the list of values; it's just one only. Okay, so let me read out the next question. Okay, the next question is how secure is using Impala? Okay, so when we started experimenting with Impala 1.0, so I mean I could not see very much security aspects added into the Impala. So, but in recent versions, what they have done is they have added more secure components around the Impala and make it more secure. Okay, then the next question is, so do we need to install Impala in all data nodes, which will be Impala master name node or Impala state store? So basically, we will have to install Impala on all nodes. So there is something called Cloudera provides something called Cloudera Manager, so which you can use to install Impala. So you don't need to install Impala. You don't need to go to each node physically, and you don't need to install Impala manually. I mean, if you use Cloudera Manager, it takes care of installing Impala on all the nodes. So all you need to do is just form a cluster using the Cloudera Manager and then start installing the Impala. So if Cloudera Manager, if you use the Cloudera Manager, it is very easy to install the Impala. Okay, so the next question is why we are showing Hive in architecture slide for Impala. Does it mean Impala works with both Hive and HDFS? So as I mentioned in the architecture slide, basically Impala uses the Hive metastore. So the metastore is basically, the metadata is, it maintains the mapping between the table and the file, and the actual mapping between the files and the actual blocks is maintained in the name node. So basically it uses, the Impala uses Hive metadata and the name node data to get the metadata details. So that's why I mentioned the Hive in the architecture slide. Okay, the next question is what is broadcast join? So broadcast join, let me take an example and explain what is broadcast join. So say assuming that you are going to join between the table A and B, okay. So the node, say the tables between A and B. So the table A's data is available in node 1 and 2, and table B's data is available in node 3 and 4. Assuming that. So what will happen is on node 3 and 4. So the table B's predicates will be executed, and the intermediate data will be transferred to node 1 and 2, where the A table data is there. So now the join will be executed on node 1 and 2, where A's data is there, and the join will happen in memory. So note that the intermediate result that is transferred to network will not be written into disk. So join will happen in memory. So the broadcast join, that what it means is the right table data will be broadcasted to the nodes where the left table data is there. So that's what I mean by broadcast join. Okay, and the next question is, so Impala currently have a constraint to have one equity predicate while joining the tables. Please suggest regarding the same. Yeah, as of now they have a restriction on the predicates. So I'm not sure about their roadmap, that they are planning to support other predicates as well. But as of now there is a restriction. Okay, so the next question is, okay, which database should be used for learning Hadoop, Cassandra, or MongoDB, or HBase, or etc. So you can learn generally about the Hadoop, the platform itself, the MapReduce program, how it works, all those things. So and then you can take an example. Cassandra, MongoDB, HBase are different ones. If, for example, HBase is built on top of a Google's big table model. So for learning Hadoop, you can straight away start with the basics of Hadoop and how MapReduce works, all those things. Okay, so the next question is, can the big data framework be used within the relational database? So I looked at the Impala roadmap. So currently their files, the Impala connects to either HDFS or HBase. So in the backend it uses either HDFS or HBase file system. But I see that they have a plan to connect to a relational database and to compute the analytical queries, to execute the analytical queries. So I see the plan there, but as of now the support is not available. So if the support is available, then it becomes very easy, because we don't need to use any kind of tool like Apache Scoop or something. So we can if all our data is available in relational database, we can straight away start using the Impala. Okay, so the next question is, okay, so since Impala stores the intermediate results in memory, what is the RAM that would be needed? How do we figure out the amount of RAM ahead of time while installing Impala, as we would not be sure about the data size in future? That's a very good question. So what Impala recommends is each node should have a 128 GB of RAM. So that's what Impala recommends. But I mean, it all depends on your use case. Suppose you want to join between two very large tables. So in that case, the right table data will not fit into the left table nodes. So by default, it uses a broadcast join type, and Impala supports other join types like partition join type. So when you execute a query, you can force the Impala to use the other join type like partition join type. So if you use partition join type, so both left and right nodes data will be exchanged between nodes. So in that case, you can avoid that memory problem. But certainly it depends on the use case. So what Impala recommends is you should have 130 GB of RAM in each machine. So that's what Impala recommends. Okay, so I think I've read out all the questions.
More questions are coming in, Muktakumar. Can you see the next one that has come up?
Right, I can see that, sir. Okay, the next question is, does Apache Scoop support all RDBMS in the market like MySQL, Oracle, etc. to transfer data in Impala? Yes, it has support for these databases. But then the thing is, it doesn't have, as of now, it doesn't have support to transfer data directly to Impala. So basically what you can do is, you can use Scoop to transfer your relation database data to create Hive tables on the Hadoop environment. Since Impala uses a high metadata store, so when you create tables using Hive, you can automatically use the tables in Impala as well. So let's answer the question. The next question is, okay, what if the number of OS users querying the data would be in thousands? So I think eBay got a lot of sellers, in fact, in millions. So was it like it was not being used by all the sellers or buyers? Okay. So again, this question is related to concurrency. So in the initial, we are actually continuing with the concurrency test with Impala. So initially we had about small clusters like 20 nodes, wherein we tested hundreds of users whether it scales well. So we are planning to set up a large scale Hadoop system and test the Impala with that. So regarding the concurrency, so we are yet to see the results. Okay, so what is the configuration of the system you used in your project? Okay, so we had about, as I mentioned in the slides, we had about 10 nodes cluster and 20 node clusters. So each node had about 16 GB of RAM, but that is very less. But so in the production environment, but we have about 128 GB of RAM. So in the test setup, we had about 16 GB. And so the joins that we tested is between the large table and multiple small tables. Okay, the next question is, okay, are there any use cases that suit Impala very well compared to others? So definitely. So as I mentioned in the learning slide, so if you want to run interactive queries over the large scale data, so you can very well use the Impala. So the existing, as I talked about the slide, the existing Hadoop technologies are suited for batch-oriented applications. And so if you look at Cassandra, MongoDB, or other HBase technologies, so they are either don't support join or they don't support SQL-like features. So if you want all these features and you want to run interactive queries on the large scale big data, then you can go and use Impala. Okay, the next question is, what is the minimum RAM size required for Impala? So the Impala itself recommends 128 GB of RAM for each node. So that's what their recommendation is. Okay, and the next question is, please tell me how to install Impala in local Windows 7 machines and how to connect with Java. So in Impala, I've given you a link, so wherein you can find out the VM image. So initially, when you want to start playing around with Impala, you can download the VM image and you can put it either through your Windows machine or Mac machine, and then you can play around with it. So basically, to start with, you can download the VM image and you can boot the VM within your Windows machine and you can start using it. Okay. Okay, the next question is, SQL knowledge is sufficient for learning Impala? Yeah, so if you just want to use Impala, SQL knowledge is fine. But then when you get an issue, if you want to debug, then you need to know about the internals. Then you need to know about how HDFS works, how Hadoop system works. So if you want to debug this existing system, then you need to know the internals. But otherwise, if you just simply want to fire SQL query and get the results, then you can, the SQL knowledge should be sufficient for that. Okay, so the next question is, can we integrate Impala with Hortonworks Hadoop distribution? So the experiment that we conducted was with on top of Cloudera Hadoop distribution. So I'm not sure whether that Cloudera has a support for running Impala on Hortonworks networks. But technically there is no issue because underlying the file system it uses is HDFS and HBase. So it doesn't matter which distribution it is. So technically there is no issues, but I'm not sure officially they're supporting that or not. Okay, the next question is Impala using MapReduce? Is it a replacement of MapReduce? No, Impala is not using MapReduce. So unlike Hive, in Hive what happens is when you execute a query, SQL-like query, so the query will get, the Hive will convert the query into a series of MapReduce programs and get back the results. So since it uses MapReduce program, Hive is basically very slow. But Impala will not use MapReduce. Instead, it has direct access to HDFS file system, and there is no MapReduce involved in Impala. Yeah, the next question, can you give me some more comparison between Hive and Impala? So basically, both are almost the same. The only difference is Hive uses MapReduce to execute the query, and Impala does not use MapReduce. So other than that, there are other couple of different, like the Parquet file format. So that is introduced as part of the Impala project. So this Parquet file format is supported only in Impala as of now, as I know, and Hive does not support that. So in terms of number of file format support, Impala supports more format than Hive. Okay, so the next question is SQL knowledge enough to start working on Impala? I already answered the question, I guess. Okay. Okay, the next question is, sorry, I will read the question. So, which will be Impala master name node or Impala state store? So name node. So I mean, you can install a name node in any of the data nodes, but as a rule of thumb, a name node should be in a separate node, so that you get a better performance. And Impala state store can be installed on the name node itself. So ideally, the name node and this Impala state store will be on a different machines other than data nodes. Okay. So the next question is, there are too many questions. I'll just read here one by one. Okay. There is a question about a data store. Is it a columnar data store? Would there be indexes? So, I mean, basically, Impala works on various different file formats. Like it can work on text format or Parquet format that I mentioned. Parquet format is a columnar oriented format, and it can also work with the RC file format. RC file format again, it's a columnar format. So it can work on a variety of different file formats that is supported in HDFS. Okay, so the next question is, earlier we were using Cloudera, but recently we changed the setup to Hortonworks. So this is also open source version, but we often face problems in both. Is there any guidelines to compare which is better in terms of ease of use as a beginning stage? So, I mean, we tested only with Impala, so we haven't used the Hortonworks framework. I mean, there is something called tests in Hortonworks Hadoop distribution, similar to Impala. So when it was in alpha stage, we started using it and we encountered issues. So we stick to Impala itself. But I can't really give you a comparison between which is better. So since it is in the early stage. Okay, so the next question is, have you used other DBs like MongoDB for POC? If yes, will it be possible for you to share the results? So we haven't used MongoDB when we started the experiments. So our use case is completely different. So basically, what we want is we want something like SQL-like feature, and I mean all kinds of SQL-like features we are expecting, like joins, other things. So we thought Impala is a perfect fit in that aspect, running real-time queries, real-time interactive queries on top of Impala. So that's the reason why we picked Impala. Okay, so the next question is Impala so well suited for running dynamic queries? Is Impala being used in most analytics platforms? Okay, so I could see in the website, Impala website, the Impala currently is used by most of the leading companies. So I think the production release, the initial 1.0 release happened in sometime in last June or July. So it's in the early stage, so still it's getting picked up. Okay, the next question, how does Impala take care of data updates between the nodes, or is it more suited for running dynamic queries on a static data set? Yeah, so updating data is a big problem in the Hadoop world itself. So primarily, as you mentioned, it is suited for static data set. But the schema is not fixed. You can just keep adding the data and you can execute the query. So the update will become a problem, but.
Due to time constraint, I request you to take the unanswered questions offline, which I will share with you through email, Muthukumar. So if you would like to sum up the session for today.
Sure. Sure, yeah. Yeah, so thank you all for attending this presentation. So if you have any questions, just shoot me an email. I will be happy to answer that.
All right, I'm really thankful to our guest speaker today for conducting this wonderful webinar. It was indeed a great session. I would also like to thank all our participants for their support in making this webinar a success. The recording of the webinar will be available on techegg.com by tomorrow. Thank you all for joining us today. Thank you, Muthukumar, for taking out time and having us for the webinar. Have a great evening ahead.